So now we are going to consider some other methods, some further methods in after the separation of variables that we considered. So say we have this differential equation to solve. Now in this case, we can play around with this and we may not find the separation of variables really easy to get. So let's use a trick here. Like, let's go ahead and multiply the equation by x. Okay, so if we do that, see here we get an x, and this will become x to the power 5. Okay, so I'm sorry, this would be y, not x, because x's cancel. And at this point, you may note that this left-hand side actually is the derivative of the quantity x times y. Okay, and that equals x to the power 5. Okay. Now, in this case, say we let this quantity xy be, say, u, then what do we get? We get that du dx is x to the power 5, and now we have the same situation, or same condition as we had for separation of variable questions. That is, we can just go ahead and get this as x to the 5 dx, and then when we integrate it, we'll get this as u equals x to the power 5. What's the antiderivative? X to the 6 over 6, and then we can leave an arbitrary constant here. Okay, and so that will be a solution. And if you want, you can have you can just write u back as xy, so that we can write the final solution as y equals x to the power 5 over 6, all right, and then plus how much? C over x here. Okay, so this will be the solution, and now we are going to discuss the domain of such a solution. Okay, but before that, let's just go ahead and develop a technique. Now let us continue further with another differential equation, say this one. Now in this case, multiplication by x is not going to yield anything really useful for us that we can use to easily solve the equation. So what we are going to do is that we are going to look at a technique, an analytical technique that will help us solve equations of this form. So now these types of equations, they are of a specific form, and the form is like this. That is, these are pretty standard used notations in differential equations. That is, px and qx are functions of x, and if I have an equation, a differential equation that looks like this, then you call such an equation as a linear equation in y. Okay, and what happens is this, that is, remember this. So remember that in our previous case, what we had done was we had used a function here, x, and such that if we multiplied the differential equation by x, the equation had derivative of a quantity on the left hand side, and we could integrate it easily. So if I have a linear equation in y, then if I did this, and I have written a proof of this in a separate lesson that's posted, so you can look that up and ask me if that is not clear to you. So say if we multiply by, multiply the differential equation by this quantity, okay, then we get derivative of a quantity on the left hand side. Let me just be more specific. That is, look at the equation. Look at the equation that we have here. Okay, that is. So we got this here. So in this case, if you identify, what you have is that px is negative 1 over x. So if I did this, that I took the integral, or if I computed this function, that is negative 1 over x dx here, okay, then what this will be, this is going to be e to the power negative ln x, or simply e to the ln x to the minus 1, right? And then that turns out to be simply x to the negative 1, because exponential and logarithm are inverses of each other. So say I did this, I multiplied this differential equation by x to the negative 1, what would I get? So here I have x to the negative 1, and then let's write it in the same style. That is, I am just pushing this x in the denominator upstairs, so that becomes x to the negative 2, and this multiplied with x to the negative 1 would give us x cubed. Now the left hand side is now the derivative of simply x to the negative 1 times y, and the right hand side of course is x cubed. Now I know that it doesn't seem that apparently clear, so we are just going to create like a formulated technique. But before that, you can notice here that now we can integrate both the sides. So on the left hand side, the antiderivative would be this, and on the right hand side it will be x cubed dx, and which gives us the solution as x to the negative 1 y equals x to the 4 over 4, x to the 4 over 4, and then plus a 4 plus a constant, okay? And when, or in other words, my y will be what? X cubed divided by 4, okay, plus c over x cubed. Okay. Now let's just notice c over x, I'm sorry. Let's notice one thing, that when we used this integration technique to obtain this function by using this criteria, we are assuming that our x is in this interval, that our x is a positive number, okay, so that we can use this integration procedure, okay. So anyways, let me just tell you the general procedure that we can obtain. That is, if you have an equation like this and you multiply the differential equation by this quantity, that is this right here, okay, then right here and here, then what you have is, and you can just sit leisurely and note that this left hand side is the derivative of simply this quantity. And how to intuitively develop that, as I told you, I wrote it in the notes, so read it and let me know if that's not clear. Okay, so here you are, and when we integrate both the sides, what we simply get is that we get that this would be the antiderivative of this quantity. Okay, now this looks like just too many symbols here, but once we do a couple of more illustrations, it will be much clearer. All right, so let's just take up some more examples and discuss this, so that it like we don't have to memorize it in this fashion. Okay, so as an example, let's take up a linear equation like this one and compare it with this general form of linear equation. So what you have is that your px here is how much? Sine x over cosine x, which of course is tangent x. Okay, all right, and then if you compute this integral, actually we call it integrating factor, and we will discuss that a little later. So anyways, so if you look at this function, and this function, it's going to be continuous on the interval negative pi over 2 to positive pi over 2, right? Okay, and also, if you recall, the antiderivative of tangent x, which here is px, or e to the integral px dx, is what here? It is, that is e to the power integral tangent x dx, and that happens to be what? E to the power natural log of secant x. Okay, and since secant x is positive on this interval, we don't have to worry about the absolute values, and this integrating factor or quantity just becomes secant of x. Okay, so if I go ahead and multiply this equation by secant of x, okay, let's do that. So I have secant of x here, secant of x, and this becomes secant square x. Okay, and let's just change this to tangent x. I could have kept that like this to begin with. Okay, so that's what we have there. Now notice that the derivative of secant x is secant x tangent x. Okay, so what we have now is that the left hand side is the derivative of simply y times secant x, and the right hand side is secant x is secant square x, as you can see. Now if we integrate this equation, what do we get on the left hand side? simply y secant x, okay? And on the right hand side I have the antiderivative of secant square x. And who is antiderivative of secant square x? That's simply tangent x, okay? So here these, what do we get eventually? Y secant x equals tangent x plus a constant. Now you can divide by secant x, okay, and get the final solution. Or let me just do that for you. So y will be, so what we have here is tangent x over secant x plus c over secant x. And how much is tangent x over secant x? That is simply sine of x, and this will be c cosine x, right? So what do we get eventually is this as a general solution, okay? All right, let me just bring it downstairs here, okay? So that's your final solution then. And now this time I'm going to make a real sincere effort to make it very simple for you. So if I have a linear equation in y, then this is the solution, and I just want to make it, or I just want to do it in a way that you don't find the solution that complicated. So to transform it in this form, what we would do is that we would divide the equation by x. So let's do so. So we have 3x plus 1 and divided by x, and then I have a y here, and this would be on the right hand side we have e to the negative 3x over 1 plus x, I'm sorry, simply x, I'm so sorry for that. Okay, so here our p will be this quantity, okay, which gives, so, and again we have to assume that x is not equal to 0. We would do this when we are integrating. At that time we will just determine in which territory would x work for us. So when we compute the integral of p with respect to x, and of course raised to the power on e, what do we get is this, it's e to the power, okay, the integral 3 over x, and then plus actually simply 3, not 3 over x, plus 1 over x, all right, dx here. So this will become e to the power 3x plus how much? Natural log of x. And now here we will, let's take our x in the interval, or assume that our x lies in this interval 0 to infinity, so that we can compute, we can take natural log of x here. And now if we did this, that is, went ahead and simplified this expression, what do we get? E to the 3x times e to the natural log of x, which is going to become e to the 3x times simply how much? X, or in other words, x times e to the 3x, okay? So once you obtain this integral, that is integral that you obtain by, or this function, and this function is obtained by raising the integral of this on e as a power, okay? So what we do is we just multiply this with y, okay, and then next thing is that multiply it with the function on the right hand side as well, okay, and then go ahead and integrate the right hand side, okay. Actually I copied wrong right hand side here. This is the one I should have taken. So right here, and then the book created a very convenient example for us, that is everybody here cancels, okay. So we are integrating only what? We are integrating only a 1, and that's going to be nx, okay. So if you go further or write it down, what do you get is this simply, that you have this equal to x, and of course we will have a constant c at the end. So we have a constant c, and when we solve for y, what do we get? We get y equals e to the negative 3x, okay, plus c over x, okay. And don't forget that our solution is valid in the interval 0, infinity, okay. All right, that's what we had assumed, that's what we had taken here. And at the same time, notice this, that so we have c over x, and I think I should have had an e to the negative 3x here as well, okay. So that's our solution with this as domain. All right. Now let's take a differential equation, a linear differential equation in y of a little different kind. That is, here we have this function fx as a piecewise continuous function, and we may call this differential equation a piecewise linear equation. So we will go ahead and solve it differently on the two intervals involved. So sorry about that. And here we have 0, 1, and I forgot to write that we are also given in this equation that, let me write that down, we are also given an initial condition in this question, or in this example, which is straight from out of your book, okay. So what we are going to do first is we are going to solve this equation on the interval 0, 1, where 0 is included, 1 is excluded. So what we have here is that we have this equals x, okay. Now, which will mean, if we go by our criteria of just getting the familiar coefficients, that is, you have this as 2x over 1 plus x square y, all right. And then here we have x over 1 plus x square, okay. So with these, we'll get our integrating factor, which is going to be e to the power antiderivative of 2x over 1 plus x squared. And of course, your book has really conveniently formulated this question, because this integral, if you substitute for 1 plus x squared, another quantity, say u, then this will become natural log of u. 1 plus x squared is positive all throughout. So there is no problem in the domain there. Of course, for the differential equation, we have a problem in the domain at x equals 1, right? Okay, so this comes out to be how much? 1 plus x squared here, okay. So on the interval 0, 1, what we have is that we have, if we just go by our criteria, we'll have y times 1 plus x square equals the antiderivative, okay, of x times what? X times 1 plus x square dx. All right. Now one moment, we have a typo here that I should have entered this value here, right? So that we have now the integral of x, okay, and sorry, and this becomes what then? X square over 2, okay, and of course plus a constant, let's call it c1. So on the interval 0, 1, what we have is this, that we have y equals this value. Now, since when t is 0, your y equals what? Y also equals 0, right? So if we make all those substitutions, then what shall we get is 0 on the left hand side. The moment y became 0, everything became 0. Actually, I should have said x, I'm so sorry. Okay, and here this is 0 plus c1. So what does this give us? This gives us that c1 is 0, right? Okay, so we have the solution on the interval 1, 0, 1. So for this we got, okay, on 0, 1 we have y x equals x square over 2, or y equals x square over 2 times 1 plus x square, right? Okay, so this is for this side, and when we go for the interval from open interval from 1 to infinity, I'm sorry, the closed interval from 1 to infinity, then let me go back and see what it was. Yes, we have closed interval from 1 to infinity. The only difference is that here we have negative sign, right? And now we are talking about on the open interval 1 infinity. All right, so going along the same lines, the solution would be what? The solution would be, let's see, we got this whole thing, and of course here we will have a negative sign, and then we have another constant, say c2. All right, or let me write the constant c2 here, and then on this interval our y is going to be this negative x square over 2 times 1 plus x square. All right, and then here c2 over 1 plus x square. Okay, oh sorry. All right, okay, so again we got 1 plus x square. I'm sorry, I'm lazy being typing here. So what we have is that the solution y as a function of x becomes, that is, just one sec please, So it is going to be again a piecewise defined solution. That is, we have the solution as this. If we are in the interval 0 less than or equal to x less than 1, and it's going to be given by this quantity if we have x as greater than 1, right? F x is greater than or equal to 1. Okay, so that's a solution. It's a discontinuous solution, of course, depending on the value of c. Since if we want to see if we can make it continuous, because we had a jump discontinuity in there, what we may do is that let's compute the limit of y as x goes to 1 from the left. Okay, so here we are. So x goes to 1 from the left of y is going to be, well, that's a matter of simple substitution. It will be simply 1 over 4. Okay. Now, on the other hand, if we compute this, I said from the left, and I'm writing from the right. Okay, that's not a very good thing. Okay, sorry about the typo. Now we are going to go from the right. Okay, and here we are. So we get this, and in that case, what we shall get? Here we are going to get negative 1 over 4 plus c2 over 2, right? Okay, now if we want the function to be continuous at 1, what we must have is this, that this quantity or the limit from the left has to be the same as the limit from the right. Okay, and which means what? c2 over 2 has to be 1 over 2, because when you bring this 1/4 here, add that to the 1/4 on the right side, you get this 1/2, and c2 becomes what? 1. Okay, so if we took, just a second, if we took c2 as 1, then this would be a continuous function of 1. That is, if we just go ahead and take this as 1 here, now we have a continuous function. Okay, so this is a continuous function, but note this, that it's not really, it's not a solution of the given differential equation. Okay, sorry, given differential equation, okay, on the entire interval 0 infinity, 1, or this interval that we had 0 to infinity. Why? Because, well, one thing you can see right here, no, not that. Okay, one thing you can see is that if you go ahead and graph this function, okay, let's go ahead and graph this function differently at the two places. So here we have, I am graphing, I mean, I can just graph it directly, but I'm just going step by step. Okay, so you have this value. Let me graph it and bring the graph back to you. Okay, so as I said, here is a graph of this function, which I just pasted in a different environment. So this is the graph on the left of 1. This is on the right. And as you can see, the function is not even differentiable at x equals 1. All right, so this is a continuous function. Of course, from 0 to 1, it satisfies the given differential equations. On right of 1, it does, but not on the entire range, or just a moment, we meant this, but not on the entire interval 0 to infinity. Okay, so here we have some linear equations. So let's just do a couple of more illustrations of these analytical methods, and then we will move on. Now let us consider a differential equation of another type. Say we have this differential equation to solve. Now here at the moment we are just going by inspection, and then we would then we would get a formulated procedure. See this 3x squared, that's derivative of x cubed, right? And this guy y squared here is the, I'm so sorry, this portion 2y, 2 times y here is the derivative of y squared. So what you can try is just seeing right here that this left hand side here is the differential of x cubed y squared. And now if you take the antiderivative, then on the left hand side we have x cubed y squared, and on the right hand side we will have a constant. Okay, so when we have a differential equation, so conveniently related in the sense that if we go ahead and take the differential of this equation, we'll get the differential equation directly. So we called such a differential equation an exact equation, or an exact differential equation. What I mean to say is that, say we have a differential equation of the type or that looks like Mdx plus N dy, where M and N are continuous functions of x and y, all right? And then we can get a function f, okay, excuse me, get a function f, okay, such that, one moment, that df equals this quantity here. Then you can see that the function, that the solution is just f equals to a constant. Okay, then we say that this differential equation is an exact differential equation. Okay, and you will see it can be solved very, very conveniently. Okay, all right, so here we go. Okay, so now let's go ahead and see. I mean, here it was, I mean, for some of us it's evident, for some of us it's not that evident. But anyways, here what we are going to do is we are going to see a well-formulated way of determining when a differential equation would be an exact differential equation. Okay, so yeah, I'm just showing that in a little geometrical sense, that here we have this differential equation given to us, and say we know that there is a rectangular region in which both these functions m as well as n, okay, have both of these have, this is important, okay, that these both have continuous partial derivatives. Okay, all right, then what happens is this, that we can now obtain a condition which will, or a test which will tell us whether this differential equation is exact or not. And if it is exact, we would develop a method of solving it. Okay, so as I said, let's assume that m and n have continuous partial derivatives available in a region, and this is sorry about that, and this is exact. Okay, so what we have is, so if it is exact, then as I just said, that we can have so we have a function f, which is a function of x and y, such that the differential of f is the same as this differential, right? Okay, now if we calculate the differential of f, if you did not take partial derivatives, don't worry, just follow along, and it's just a little procedural at the moment. Sorry about the pronunciation. Okay, so here we got this plus df dy, okay, dy equals how much? This equals right here this quantity. Okay, so what we get then is that df dx is m, all right, and at the same time we get df dy equals what? I'm just going to cheat in this copying. That is df dy equals n at xy. Okay, sorry, n of xy. All right, so if this is the case, then you know that the order of derivatives, when the partial derivatives exist and they're continuous, that doesn't really matter. So if we differentiate it with respect to y, okay, what we will get, d2f dy dx, and that is going to equal, and I'm going to just shorten the notations. Okay, so this is dm dy, right? And at the same time here, if I took the second derivative of f, or if I took the derivative of df dy or with respect to x, okay, then what this will be, dn dx. Okay, so, and actually this becomes a condition which works both ways. I'm not proving it both ways, and actually when we visit the method of solution, you know, that will be proven in a sense. So first of all, let's notice that this quantity and this quantity, they are equal. So what does this give us? That in the case this is exact, what we will have is, this will be a criteria that we will use, that dm dy, that equals what? dn dx. Okay, all right. Now, as I said, it works both ways. Okay, and I'm not proving the other way around, but when I'm going to show you an example, the example will illustrate how the other way around works. So let's work on this differential equation, and first we are going to show that this is an exact differential equation, and then we will just develop a method of solving this differential equation. Okay, so I have m and n equals these quantities, with m and n having their usual meaning. So let's first verify that dm dy, which is, now I'm differentiating partially with respect to y. That means I'm treating x as a constant, so I get 0 plus 0. All right, and then minus, what we have is, we can use the quotient rule here. And remember this again, we are treating x as a constant. All right, so first of all, in the quotient rule, what we would do is, we'll square the denominator, okay? And we are differentiating only with respect to y. So derivative of y here is how much? 1. So we differentiate the top and just write the bottom as it is, and then minus the top times the derivative of the bottom function here with respect to y. What that will be? That will be 2y, right? Oh, sorry, 2y, okay? So this is going to be, notice this, 0 plus 0 is 0. So you have, actually, if I take negative sign inside, then this would be negative and this part would be positive. So what you get is, here, this would be negative, means both these signs become what? They become negative, okay? And this part is positive, so I get plus 2y square, okay? And then on the bottom I have x square plus y square, quantity squared, and so this will be 2y minus y square would be just positive y square, okay? So this is what this whole thing becomes, okay? I'll erase this because this got cancelled here, right? Okay, now let's look at dn over dx, okay? And I'm just going to talk with you through this because it's pretty similar. So notice this, n is this quantity. Let me rewrite it here. So we are differentiating with respect to x, so the derivative of this part would of course be 0, okay? And then what I have next I have this, I'm differentiating this quantity with respect to x. Now notice this, it'll be similar to different derivative of this quantity with respect to y, all right? Other than that, we had a negative sign there, but let's not worry about it at the moment. So if we go by that criteria, what do we have is x and y, they will simply switch places, which doesn't matter over here. But here, what do we get? Here we simply get negative y square plus x square, okay? So our verification is complete that dm dy is the same as dn dx. Now let's see how do we get our function f. So if you remember, if f equals a constant is a solution, that would mean what? We just did it a short while ago, right? Okay, this means df dx, okay, dx plus df dy, okay, so df then dy equals 0, which gives us what? That df over df dx is going to be m. So what does it mean is that df dx is going to be m, and who is m? M is this right here. So what we are going to do now is we are going to obtain f by integrating this quantity with respect to x. That means we'll treat y as a constant. So when we do that, what shall we get our f as? Or we may write it at fxy. Okay, so we get that as, here we have natural log of absolute value of x, 1 over x squared. What is the antiderivative with respect to x? Negative 1 over x. Now here, see this is of the type constant divided by x squared plus constant square. Now remember this, that this would simply be, here y is a constant, so it will be y over y, and then tangent inverse of who? see, I'm taking the antiderivative with respect to x, treating y as a constant. So this is what I would get. Okay, and how did I get that? Let me just recall that quickly for you. I got it from the rule that 1 over u is square plus a square with respect to u is what? 1 over a tangent inverse of u over a. Okay, and plus a constant, and notice this, that I have forgotten that constant over here, right? Okay, now here we were integrating with respect to x and we were treating y as a constant. So the quantity that we will get as a constant, or in other words independent of x, is going to be a function of y. All right, okay, so now we have almost determined this fxy. What is left is I have to determine this function h of y, which will serve as a constant there, right? Let me just erase this here. Okay, so how do I obtain my h of y? So if I look at this thing here and I have to obtain h of y, so now to get df dy, what we are going to use is that df dy is going to equal how much? N. All right, okay, because notice this differential here, this quantity here has to equal what? The quantity n from the original differential equation. So we have this. So when we are differentiating it with respect to y, for this portion we will have a 0. Okay, why? Because that is a function of x. Then minus, and I was a little lazy in my calculations, so we didn't do anything wrong, but I could have gotten rid of this excess portion. Okay, so here tangent inverse x over y, and we are differentiating f with respect to y. So what would that give us then? And now we have to differentiate this with respect to y, treating x as a constant. So we will go by chain rule. So derivative of tangent inverse is what? Derivative of tangent inverse of a quantity is going to be 1 over square of the quantity, right? Right here. And then what? The derivative of the quantity, and the quantity here is and the derivative with respect to what? The derivative with respect to y. So this is what we would get here, and then what we are going to get is dh dy, or we can just write that in a regular form, dh dy, because h is exclusively a function of y. Okay, and that has to equal how much? N. And how much is n? Let's write n down. We already have n here. So this is what this has to be, right? Okay, so let's see this here. For this one, okay, I know it's hard to talk it through completely on a screen, but we are trying to communicate the best we can. Okay, so what this would be, this is like a constant over y, so this derivative would be negative x over y square. Okay, all right, okay, so that's what this would be. And then let's just go one more step. See, on the bottom I'll have x square plus y square. This negative will become positive. Okay, or let me just do this algebra a little more, just cost us probably a minute. Okay, and YouTube is not charging us, so that's okay. So here, see, what is this portion here? This is x square, okay, plus y square over y square. Okay, all right, and again, this negative, they became positive, so that's what we got. Now this y square and this y square, they will cancel, right? Okay, so what do I get then? X over simply x square plus y square, and then plus dh dy equals that n written on the right hand side. Now what will happen on the two sides? This will cancel that. So as a consequence, what do we get? We simply get dh dy as y e to the y. So now this turned out to be actually a review of many things. I just happened to take this one. So anyways, so h is what? The antiderivative of y times e to the y. Okay, and what we can do is we can go ahead by integration by parts. So what is it? You know, remember we did that in an example a short while ago. So that will be y e y, okay, minus e to the y. And now we will have a constant, and this constant will be free of any variables here in this situation. So where is our function? Fx y was this that we were determining. Okay, so fxy is this, and this is what? Hy is this. Okay, we can write that equals to 0, or that equals another constant little c, say, and I can write my final solution as this whole expression equals a constant d. All right, so this is just you know, methodological formulation, and what we have done is that we have reviewed many techniques from calculus at the same time, have gotten a flavor of, you know, putting these things in the context of changing quantities. Okay.